Okay. So I'm sorry that half an hour of the recording is lost, but let's continue with this thing here. So we have proved an important result which we will use, but let's continue with this Hensel's lemma. Let's start with the polynomial f, which is primitive, and suppose that f bar is a product of two polynomials g and h with coefficients in the residue field which are relatively prime. And the proposition says that then there exist two polynomials capital coefficients in my ring OV which have the following properties. What are the properties? First of all, the degree of this capital G should be equal to the degree of little g. Secondly, capital G should be congruent to little g modulo PV. Similarly, capital H should be congruent to little h modulo PV. And finally, F should be equal to the product G times. So this is fantastic. If somehow you are able to factor f bar as g times h, then basically you are able to factor f as g times h with g and h having some additional properties, with g reducing to little g and h reducing to little h, and the degree of capital G being the same as the degree of little g. This is kind of magic, right? For example, I mean, ZP is a huge ring in some sense, but FP is a small field. We can factor polynomials in FPT more easily than in ZP. So if I'm given some F with coefficients in ZP, then F bar will have coefficients in FPT, and I can try to factor it in this ring FPT. And such a factorization somehow gives rise to a factorization GH in this ring ZPT. So that's very interesting and very useful. So let's look at a proof. Look at the proof of this result. So let's just use the shorthand R for the degree of little g and S for the degree of F minus R. So that's going to be bigger than the degree of H because degree of F bar is less than the degree of F, right? Because the top coefficient of capital F may be divisible by our uniformizer. It might be congruent to 0 modulo P. Now, little g and little h are given to me, so I can always find G naught and H naught in OVT, which lift little g and little h, and moreover, which have the right degree. The degree of G naught should be equal to R, which is, of course, by definition, the degree of little g, right? And this degree of H naught should be equal to, should be less than S. And we know that degree of H is less than S. Okay. And we clearly have F equal to, F congruent to G naught, H naught, modulo PV. That's because G naught is congruent to G, H naught is congruent to H, and F bar is congruent to G times H, right? So these obviously imply that F is congruent to G naught times H naught. Now this is nothing, I've not done anything, I've just renamed things a little bit. We just have renamed, okay, so the difference is that little g and little h had coefficients in KV, whereas G naught and H naught have coefficients in OV. I mean, they lift these G and H, etc. But we are basically just renaming a few things. The real work starts now. So the first thing we would like to do is to find G1, H1 with coefficients in OV. Now find polynomials G1, H1 having this list of properties. What are they? The degree of G1 should be equal to R. The degree of H1 should be less than R. S. G1 should be congruent to G0 modulo pi. So pi, remember, is a uniformizer. So that pi OV is equal to PV. And right. So, or another way of, I mean, some people prefer writing this as that PV is the ideal generated by pi. So we want, I've been writing mod PV. I mean, that's the same as writing mod pi, of course, right? These are the same. So I want G1 to be congruent to G0 modulo pi and H1 to be congruent to H0 modulo pi. These are just 4 of the conditions, but the main requirement is that F should be congruent to G1 times H1 modulo pi squared, not just pi, but pi squared. Modulo pi, I already have this thing. F is congruent to G0 times H0. But I want now a factorization which is valid modulo pi squared and not just modulo pi. Okay, so I have to find this G1, H1. Now these first 4 conditions, to satisfy these 4 conditions is easy. You just take any A1, B1 with coefficients in OVT such that the degree of A1 is strictly less than R, the degree of B1 is less than S, and you put G1 equal to G0 plus A1 pi, and you put H1 equal to H0 plus B1 pi. Okay, so if you do this, all of the first 4 conditions, these 4 conditions, will be satisfied. Because what are those conditions? The conditions are the degree of G1 should be equal to R, the degree of H1 should be less than S, G1 should be congruent to 0, not 0, to G0 modulo pi, H1 should be congruent to H0 modulo pi. And these things ensure these 4 conditions. In fact, you could take A1 and B1 to be the 0 polynomials, and still these 4 conditions will be satisfied. But if you take the 0 polynomials, if you take A1 to be 0, B1 to be 0, there is no guarantee that F is going to be congruent to G1, H1 modulo pi squared, which is what we want. So this is what, so you have to choose these A1, B1 a little more smartly. Okay, so how do we choose them? So notice that F can be written as G0, H0 plus F1 times pi. For some F1 in this of degree less than R plus S. R plus S is the degree of F, right? That's how we have defined it. R is the degree of little g, and S is defined to be degree of capital F minus R. So degree of F is actually equal to S plus R. So why can I write it like this? Because F is congruent to G0, H0 modulo pi, right? So the difference F minus G0, H0 is some multiple of pi. And what can be the degree of this polynomial f1? It has to be less than r plus s, because that's the degree of f. So that's not difficult. Now, these g1, h1 that we have defined here, if I multiply them out, what do I get? G1 times h1 is g0, h0. That's a product of these two terms. Then there are these cross terms, g0 b1 and h0 a1. Let's see whether that's okay. h0 a1, I have written it later, but g0 b1 plus h0 a1 times pi, right? This pi is there, here and here. And then there's going to be this term a1 b1 times pi squared, but I'm working modulo pi squared, so I don't write that term at all. That was the term a1 b1 pi squared, but that vanishes modulo pi squared. So now I've got two expressions for g1 h1, right? Not two expressions, but no, I've got an expression for f, I've got an expression for g1 h1. And if I want f to be congruent to g1 h1 modulo pi squared, then what should happen? I should compare these two expressions, this and this, right? So here, these things are the same. And here I have f1, and here I have this object here. So if they have to be congruent modulo pi squared, this f1 should be equal to this thing here. So the requirement that f should be congruent to h1, g1 h1 modulo pi squared is equivalent to f being congruent to this thing here. That is what we have to ensure. Now this must ensure this. Remember, I said choose a1, b1, and they will automatically satisfy the first four conditions. But the important condition, which was that f should be congruent to g1 h1 modulo pi squared, that is satisfied only if I ensure this thing here. Must ensure this in order to get this. Okay, how do we ensure this? So we know that the GCD of G and H is 1 in this ring KVT. So there exist alpha and beta such that alpha G plus beta H is equal to 1. Now write alpha as A plus C times G. This A is the remainder, and this C is the quotient. So I'm basically dividing alpha by G. I can do that, right? This ring is Euclidean. I can divide alpha by G. So I'll get some remainder A. So the degree will be less than the degree, strictly less than the degree of G. And there's some quotient C. And then I take B. I've got an A here, and I define B to be beta. Remember these, I get alpha and beta here, and I take B to be beta plus CH, the same C. And H, G and H I already have, they are given to me. So I take alpha to be this, beta to be this, A to be this, and B to be this. Then what I'll have BG plus AH is congruent to 1, is congruent to F1 modulo pi, and degree of B is less than S, because degree of F1 bar is less than R plus S. Okay, so there are some small check-ins which you need to do in order to justify everything. Now you take A1 to be any lift of little a1. Why is it called little a1? There's no little a1. There's just an a. Take a1 to be any lift of a of degree less than r, strictly less than r, and take b1 to be any lift of little b of degree less than s. And that will ensure that f is congruent to G1 times H1 modulo pi squared. So this is the first step. Just as in the usual Hensel's lemma, which we have proved, the next step is essentially similar. We'll have to repeat this. So let me stop here for a few minutes to see if there are any questions. Otherwise, I'll continue. Okay, if there are no questions, I'll continue. Okay, so what is the next step? So suppose that for some n, I found, and every I in 1 to n, I found polynomials gi, hi with coefficients OV, such that the degree of gi is r, the degree of hi is less than s. Gi is congruent to gi minus 1 modulo pi to the I. Hi is congruent to hi minus 1 modulo pi to the I. And f is the product of gi and hi modulo pi to the I plus 1. Then I want to go from n, this n, I want to replace it with n plus 1. I want to go from n to n plus 1 and find polynomials n plus 1, n plus 1 satisfying or similar conditions. So I begin by writing f as gnhn plus fn plus 1 times pi to the n plus 1. That's because of this, right? I can write f like this. And then I take an plus 1 and bn plus 1 to be polynomials OVT such that the degree of an plus 1 is strictly less than r, the degree of bn plus 1 is less than s, and I have this thing. Yeah. Now that is possible because the degree of g and h, the GCD of g and h is equal to 1. This is what we have done earlier. In the case step 1, this is what we had done. And exactly the same thing works here. Then you define gn plus 1 to be gn plus an plus 1 times pi to the n plus 1. Similarly, hn plus 1 is hn plus bn plus 1 times pi to the n plus 1. Then obviously we will have gn plus 1 is congruent to gn modulo pi to the n plus 1. hn plus 1 is congruent to hn modulo pi to the n plus 1. And f is going to be congruent to gn plus 1 times hn plus 1 modulo pi to the n plus 2. Okay? So in other words, these GNs form a sequence which converges to some GG. Similarly, these HNs form a sequence which converges to H. The degree of G is going to be R. The degree of H is going to be less than S. And this G is going to be congruent to little g. Capital H is going to be congruent to little h modulo pi. And F is going to be the product, G times H. Okay. So this is the proof of Hensel's lemma, and it allows you to factor. So basically, I mean, something which is not very difficult to. It's not something very difficult to remember. Now, the proof is not what you have to use all the time. It's the statement, and the statement is easy to remember. If you have a polynomial f in OVT, which is primitive, if you have f bar is g times h, okay, modulo pi, and GCD of GH is equal to 1 in, of course, KVT. These are the hypotheses, and this implies that they exist G and H, such that F is equal to G times H. The degree of G is equal to the degree of little g. Not just that, but G is congruent to little g modulo pi. H is congruent to little h modulo pi. And what else? That's all. That's all. Yeah. These are the things you get. So this equality takes place in OVT. This is sense. Okay, so here are some consequences. Suppose I take a polynomial with coefficients in my field K. This K is what kind of field is it? Complete for a discrete variation. So the variation is essential in the sense that it's not a trivial variation. So I have a polynomial with coefficients in this field K. But if the constant term happens to be the subring OV, then in fact the whole polynomial has coefficients in the subring OV. That's kind of magical. It's only, I mean, I can't write down a polynomial. Of course, it has to be monic and irreducible. So I can't write down, every time I write down a polynomial A0, so this is an OV plus an t to the n. So an should be 1 because I want the polynomial to be monic. But if it's irreducible, then automatically these AIs are in OV. That is what is being claimed. Here it is. If f is an t to the n, and this an is equal to 1 because it's a monic polynomial, right? And AI, the other AIs are in K. That's what is given to me. They are in K, and I'm told that it's irreducible, and I have to conclude that these AIs are in OV. Now, if AI is not in OV for some I make this assumption or into a contradiction. I want to prove that all AIs are in OV. Let's see what happens if they are not. Oh, let's echo again. So I don't know what to do. Okay, can you hear me still? Yeah, can you hear me or? Yeah, okay, good.
Echo is coming in.
And there's no echo, I hope. There's no echo. Okay.
Sir, have you plugged into another?
For the sake of getting a contradiction, let me assume that one of the AIs is not in OV. For some I, which is between 0 and n. Now, although the coefficients AIs may not be in OV, but some pi to the appropriate m times AI are all in OV, of course, right? Because this K is, after all, just OV, and you invert pi. So the only things in the denominator are powers of pi. And there are only finitely many denominators. If I multiply by a sufficiently large power of pi, then they will become integral. They will become elements of OV. So here is pi to the m times f is in OV for some m. But I want m to be just right in the sense that I want pi m times f to be a primitive polynomial, which means that at least one of the coefficients should be a unit. I don't want to multiply by a very, very high power of pi such that everything becomes divisible. All coefficients become divisible by pi. No. I mean, I just multiply by a power of pi, enough for the coefficients to be in OV, and such that one of the coefficients is a unit. So the smallest possible m is what I should take. Okay, then let's call capital F this new polynomial, pi to the m times f. So it will have some coefficients bn, b0, etc. Where bi is, of course, pi to the m times ai. Now let r be the smallest index such that pi to the m r, ar, I said one of the coefficients is an OV star. One of the coefficients is a unit. So let r be the smallest index such that this is br, right? Such that br is a unit. So this r cannot be 0 because f0 is already in OV, and I multiply it by pi to the m fv for some m strictly positive, then this cannot, of course, be in OV star, right? At best, f0 is itself in OV star, but then when I multiply it by some power of pi, it will fail to be in OV star. So this r has to be strictly positive because f0 is in OV. Now, when I reduce this polynomial f modulo pi, what do I get? I get f bar, which is congruent to t to the r, because a0 or rather b0 plus b1t up to br minus 1 t to the r minus 1 plus br t to the r plus so on. That's what the polynomial looks like. All these things are divisible by pi. So when I reduce it modulo pi, all these these terms will disappear. My f bar will look like br bar tr plus br plus 1 bar tr plus 1 and so on. So of course I can take t to the r outside, and that's what I've done. T to the r outside, and inside I'll get this expression br bar plus 1 bar and so on. I call this polynomial t to the r, I call it g. And I call this polynomial inside, I call it h. So now I've got f congruent to g times h modulo pi. I've got a factorization of f modulo pi. And GCD of g and h is 1. Why is it 1? Because what are the divisors of g? I mean, g is t to the power r. The only possible divisor is t. But h is not divisible by t, because what is h of 0? H of 0 is br bar, which is not 0 in kV. Why not? Because br is, by hypothesis, it's a unit. So h is not divisible by, the only divisor of g essentially, which is t, and therefore g and h are relatively prime. So basically the only divisors of g is not a divisor of h, and therefore they are relatively prime. So what does Hensel's lemma tell you? It gives you two polynomials g and h with coefficients in OV. The degree of g is r, and f is g times h. But this contradicts the fact that F is irreducible in KT. Why did we get this contradiction? We got this contradiction because at some point we must have assumed something which is wrong. And what did we assume? We assumed that these AIs are not in OV. At least there's some I for which AI is not in OV. So this contradiction forces us that, this contradiction gives us that AI is in OV for all I, and this is the same as saying that F is a polynomial with coefficients in OV. So F monic, oh, okay, so F, where is it? It's in KT. It's monic, it's irreducible, and F of what? F of 0 is in OV. These things imply that F is actually in OV. That was the statement. Huh? Okay, so the next statement is that if I have a valued field, so it's a K is a field, V is a valuation, and I take a finite extension of this K. And the question is, does L have a valuation W which sort of extends the valuation V on K? So basically, I have, of course, this K, and this is contained inside L, and this valuation V is basically a map to R union plus infinity. And the question is whether I have something here, W, which is also a valuation, making this diagram commute. That is the question. It's a natural question. And we need it only in this situation where the valuation is discrete. The value group is isomorphic to Z. And the field K is complete for this valuation V. The claim is that in this situation, there is a unique valuation W on L, which extends V in the sense that which makes this triangle commute. There's a unique valuation W on L extending V, and in fact, you can take, there's a formula for that W, which is that W of X is equal to the V of the norm from L to K of X, the whole divided by the degree of L over K. Now this norm L over K is a map from L to K, which I remember was explained in one of the tutorials. And the basic property, one of the basic properties is that norm of a product is the product of the norms, right? So that's the norm which is being used here. Okay, so this is what we have to prove, that if the valuation is discrete and K is complete for that valuation, then there's a unique extension W to, as a value, there's a unique valuation W on L, which extends the valuation V on K. And there's this explicit formula. Okay, so the uniqueness part is easy. So if I have two extensions, W and W2, both extending the valuation V on K, then I can view these valuations on L as norms on the K vector space L, because they satisfy the conditions, the axioms for a norm. The the axioms were something like this: the norm is 0 if and only if the vector is 0, and the norm of X plus Y is less than the norm of X plus the sum of the norms, and finally the norm of some alpha times x is equal to the absolute value of x times the norm of x. I mean, something like this, right? So these if they are valuations, then they'll satisfy these conditions. Not quite these valuations themselves, but rather the norms associated with these valuations. Remember? So we have discussed how valuations are related to what I'd called un-Archimedean norms. Anyway, so if there are two valuations W1 and W2, extending the valuation to V on K, then the associated norms on the K vector space L will be what? They will be equivalent, because any two norms on a finite dimensional vector space are equivalent. That's what we have just proved. And if the associated norms are equivalent, then the valuations themselves are equivalent. They're equivalent, okay, but are they equal? Now, what I know is that they extend the same valuation V on K. So the restriction to V, restriction to K are equal. Therefore, the multiplication, the constant which appears in the definition so the constant turns out to be 1 because it's 1 for x and k. So the two valuations are actually the same. Hello, can you hear me now? Yeah, I think you can hear me now. Okay, now this is going to be, I hope there is no echo now. Okay, good. Right. So let's come back to this definition. I have W of x is, let me write it here, W of x is the valuation of, you take, now x is in L, in this extension L, you take the norm from L down to k of this x, take its valuation and divide by the degree of L over k. That's W, the definition of W. So what do we have to verify? We have to verify that W is a norm, or rather it's a valuation on L. That's one of the things. And that the restriction of W to K is equal to V. Now, this last thing is very easy. Let's see. Okay, so first of all, the norm is multiplicative and V converts, V is also multiplicative in some sense. I mean, V is also a homomorphism of multiplicative monoids. So W of x plus x times y is W of x plus W of y. That's completely obvious, right? If it's not, let me clarify it here. So you have these two things, norm. I'll just write n, capital N, or okay. N L over k xy is n L over k x times n L over k y, and V of A times B is V of A plus V of B, right? So V of n L over k of x times y is going to be V of, okay, D times, it's the same thing. Or I have to divide by D, so V of the norms are going to be is multiplicative, so it should be n L over k x times n L over k y divided by D, and that's equal to V of n L over k x divided by D plus V of n L over k y divided by D, but that's W of x plus W of y. Okay, so this was easy. I mean, I don't know why I did it. So this is what we get. The next thing I want to check is that the restriction of W to K is V. So I take an X in K, then what is the norm from L down to K of X? It's X to the power D, where D is, recall, it's the degree of L over K. So W of X, by definition, is going to be V of X to the power D divided by D, which is V of X, and we get this. So the main thing is to check this property of valuations, that the valuation of a sum is bigger than the smaller of the two valuations, the valuation of the two summaries. So of course, in order to prove for this inequality, I can assume that X and Y are different from zero, right? Because if one of them is zero, then the inequality is not very difficult to prove. It's actually an equality, right? Okay. So we assume that X, Y are in K star, and up to interchanging X and Y, we may also assume that W of X is greater than W of Y. And then we have to show that W of X plus Y is greater than W of Y. I mean, this inequality says that the valuation of the sum is bigger than whichever is smaller. So if W of Y is smaller, I have to prove that the valuation of the sum is bigger than W of Y. Now this W of X is bigger than W of Y can be rewritten as W of XY inverse is positive, and to show that W of X plus Y is bigger than W of Y, I know that W of X plus Y is W of Y plus W of 1 plus XY inverse. Because I can write XY as what Y times 1 plus XY inverse. So in order to show that this is bigger than this, I have to show that this thing is positive. Now, what I'm given is that W of Z, let's call it Z, this XY inverse, let's call it Z. I'm given that W of Z is positive, and what I have to prove is that W of 1 plus Z is positive. So we have to show that W of Z is positive implies that W of 1 plus Z is positive. That's what things come down to. Okay, so let's get going. So I take the minimal polynomial of Z over K, and let's call N the degree of this polynomial. So it's it's also equal to the degree of, you have the field KZ, it's an extension of K, and this degree is N. It's the degree of Kz over K. And now you have to know a little bit about the minimal polynomial, that the norm from Kz to K of Z is related to the constant term of the minimal polynomial. Here is the constant term, here is the norm, except that there is some sign which depends upon the degree. So it's -1 to the power n times. So this is what I've written here. So if I know the minimal polynomial, I know the norm. But what I need is a norm from L to K of Z, not from the norm from Kz to K. But that's easy. I mean, that is just you raise everything to the power m, where m is the degree of L over Kz. So my hypothesis that W of Z is positive implies that f of 0 is in OV, because see, this f of 0 and this norm are basically the same thing up to this sign. So the W of Z is the valuation of this norm. The valuation of this norm is positive, means that valuation of F0 is positive, which means that F0 is in OV. Okay, so here's the reason why W of Z positive means that F of 0 is in OV. Okay. Fine. Now, the minimal polynomial is, of course, an irreducible polynomial, and its constant term is in OV. This is what we have just checked. So the whole polynomial will have coefficients in OV by what we have proved just now. In particular, f of -1 is going to be in OV. If I have a polynomial in OV and some a OVT and some a in OV, then of course f of a is in OV, right? But what is the minimal polynomial of 1 plus z? It's ft minus 1. And the norm of 1 plus z is f of -1. So the constant term of this, which is, you put t equal to 0. So it's f of -1 to the power m. And therefore, the valuation of 1 plus z is positive because this valuation is basically related to the norm of 1 plus z, which is related to f of -1, and we have seen that f of -1 is in OV. Okay, so that's what establishes the claim. We had reduced it to proving that W of z positive implies that W of 1 plus z is positive. So we use this hypothesis to say that the norm L over K of Z is in OV. And we saw that this implies that norm 1 over L over K of 1 plus Z is also in OV. And of course, this implies that W of 1 plus Z is positive. Okay, so that's the summary of the proof. Okay, so then now what has happened? I have my field K, I have a valuation V on K, then I have this extension L, and I get a unique valuation W on L, of course, under the assumption that V is discrete and K is complete. Now it's easy to see that W is also discrete. And also, we have seen that L is L is complete. Remember, we had seen that any two norms are equivalent and E is complete with respect to any of the norms. So I get complete, L is complete for this discrete valuation, W. Okay, so just as I had the ring OV here, I get the ring OW here, which has a principal ideal PW, and there's a residue field KW, which is OW upon PW, just as I had PV here and KV here, which was OV modulo PV, right? So the picture is that I have, sometimes people draw it like this. I have OV here, which is a subring of K, and then I have a finite extension L, and I have OW here, which is a ring contained inside L. Okay. So the next proposition says that this OW is the integral closure of OV inside L. Everything inside L, which is integral over OV, is contained in OW, and everything in OW, and everything in OW is in fact integral over OV. The two things are the same. Integral closure of OV in L and OW are the same. Okay, so here's the proof. So I start with a Z in OW. By definition, it means that W of Z is positive. So that means that the minimal polynomial has coefficients in OV. That's what we have seen just now, right? That if W of Z is positive, in the course of this proof, we had seen this, right? We had seen first that W of Z is positive implies that the constant term is in OV, and then it's irreducible. So the whole polynomial is in OV. Okay, so where was it? Yeah, the polynomial is in OV, it has coefficients in OV, and therefore Z is integral over OV because this is a monic polynomial, right? Why is it monic? Because it's what is it called? Minimal polynomial of Z. Minimal polynomials are always, of course, monic, and they are irreducible. But I'm not using the irreducibility here. I'm just using the fact that it's monic and has coefficients in OV, and therefore this Z is integral over OV. Done. Now, so I have to prove the converse. Meaning if something is integral over OV, then it's in OW. So something is integral over OV means that it's minimal polynomial. I mean, something is integral over OV means that its minimal polynomial has coefficients in OV, which means that its norm of this element Z is going to be in OV, because this norm is basically just the F0, where F is the minimal polynomial, right? Up to sign. Up to sign, it's F0. And if the norm is in OV, then W of Z is positive, because W of Z is V of norm L over K of Z. If this is in OV, implies that V of that thing is positive, so W of Z is positive. So Z is in OW because its valuation is positive. So that was easy. Next, let me see how much time I have. Oh goodness! So I have to be a little quicker now. Okay, so here what I'm saying is that if I have a field which is complete for a discrete valuation, and if I take the algebraic closure, then there's a unique valuation V bar on K bar, extending the valuation V on K. So this we have seen for finite extensions, but now I'm saying I have K, I have the valuation V, which takes values in R plus infinity, but the image is discrete. And then I have K bar, I have this inclusion, and I'm saying there's a unique valuation here, V bar. I'm not saying that it's discrete. I'm not making any statement about this being discrete. So it's usually not discrete. This one is discrete. That's what we have. And K is complete for this discrete valuation. These are the hypotheses, and this is the conclusion that there's a unique valuation V bar extending V. Now this follows from the fact that this K bar is actually the union of finite extensions of K in K bar. And V extends to every finite extension uniquely. So there is no problem. I mean, they all give rise to a valuation V bar on K bar. Now, if I have two elements of K bar, which are conjugate over K, then V bar of X is equal to V bar of X prime. Okay, how do I check that? They are conjugate means that there is some K automorphism, sigma. Sigma is an automorphism of the field K bar, leaving everything in the field subfield K fixed pointwise, which takes X to X prime. That's what it means for them to be conjugate over K, right? But then I can compose, I have my K bar, this is sigma, and I'm given this V bar. I can take the composite, which is what? Which is V bar sigma like this. Yeah. Then this V bar sigma is also, of course, a valuation on K bar extending V. So it has to be equal to V bar because so the uniqueness of X extensions. So V bar of X, which is V bar sigma of X, but sigma of X is X prime. So I get V bar of X is equal to V bar of X prime. That's what was being claimed. So I'll just take a few more minutes because I want to finish this important lemma before the next session, right? Or, okay, forget about it. I'll do it next time. I think you might have some things planned. So I'll finish right now, unless there are some questions. Are there any questions? Yeah?
Sir, if K is not complete.
Okay, if not, I'll finish here today.